right, so now we can look at multiplying two matrices together. There are certain requirements on the sizes of the matrix in order to multiply these together. The first matrix, and there's a left matrix and a right matrix. Okay, so it doesn't matter how those matrices are arranged. So when I talk about the first matrix, I'm talking about the one on the left, the second matrix, the one on the right. That first matrix should be, if it's size m by n, then the second matrix must be a size n by p, where m, n, and p represent any numbers, right? But the focus here is what I'm saying is that the number of columns of the first matrix should correspond to the same number of rows in the second matrix. So the first matrix should have the same number of columns as the number of rows of the second matrix, okay, in order to multiply these together. If those do not agree, if they're not the same, then you cannot multiply those two matrices together. Okay, let's look at an example here. So we're trying to multiply two matrices to find A times B. Okay, our matrix A is a let's find the size. We've got 2 rows and 3 columns. So matrix A is a 2 by 3. And matrix B has 3 rows, 3 columns. So matrix B is a 3 by 3. Okay, so now the question is, can I multiply these together? In order to multiply them together, I must have the same number of columns as the number of rows in matrix A and B. Okay, I do. These are the same numbers here that I've circled in red. So that means I can multiply them together. Okay, and the product, by the way, the product will be a matrix of size m by p. That means that the product will be a matrix that will have m rows and p columns. So in this case, my product, my answer will be a matrix that is a 2 by 3. We'll have 2 rows and 3 columns. Okay. All right, so let's take a look at how this will work. So when I'm multiplying, this is different than the scalar multiplication. Okay, with scalar multiplication, all I was doing is multiplying each entry of the matrix by a number. Okay, this is going to be different here. The reason that the same number of columns in matrix A must be the same number of rows in matrix B is that I'm going to be multiplying the rows by the columns. All right, so I'm taking the first row in matrix A and I'm multiplying it by each column in matrix B. And each time I multiply that row by a column, that becomes a corresponding entry in the resulting matrix. Okay, so here's what we got. All right, so A times B will be a 2 by 3 matrix. And this first entry is found by multiplying the first row of matrix A by the first column of matrix B. And when I'm multiplying this row and the column, I'm doing a vector multiplication. Okay, I'm doing a vector multiplication to where I multiply each corresponding entry. So 1 times 1, 3 times 4, 4 times 2, and I'm adding them together. It's the sum of the product of each corresponding entry in the row of matrix A times the column of matrix B. Okay, and maybe you want to come out to the side and do some scratch work, right, to keep it straight in your head. All right, so we're saying 1 times 1 plus 3 times 4 plus 4 times 2. That gives me 1 plus 12 plus 8, which is 21. That is my first entry of my matrix A times B. Okay. All right, so I'm going to continue doing that. I'm going to continue multiplying that first row by all of the columns in matrix B. Right, so I'm going to do the same thing this time multiplying row 1 of matrix A times column 2 of matrix B. So that is 1 times 3 plus 3 times -1 plus 4 times 4, which is 3 plus -3 plus 16, which will equal 16. That is my second entry in my matrix AB. All right, so we'll keep repeating this procedure until we find all of those 6 corresponding entries in matrix AB. All right, next I'll multiply row 1 of matrix A times column 3 of matrix B. 1 times -3 plus 3 times 2 plus 4 times 1, which is -3 plus 6 plus 4, which is 7. Okay, and so now what we'll do is we will, since we've multiplied the first row of matrix A times all of the columns in matrix B, now we'll move to the second row of matrix A and multiply that second row times all the columns in matrix B. All right, so here's our second row, and we'll multiply by the first column. That is -1 times 1 plus 2 times 4 plus 0 times 2, which is -1 plus 8 plus 0, which is 7. And now we'll do the same thing with column 2. -1 times 3 plus 2 times -1 plus 0 times 4, which is, say, -3 plus a -2 plus 0, that will be a -5. Okay, and then finally, we've got the second row of matrix A times the third column of matrix B. -1 times -3 plus 2 times 2 plus 0 times 1, which is 3 plus 4 plus 0, which is 7. So this gives us our product, our new matrix A times B, 21, 16, 7, 7, -5, and 7. Now you may want to ask yourself, would I get the same matrix if I were to multiply B times A? All right, you may want to take a second, try it out, pause the video, and see what happens. Okay, I'll let you pause this. Okay, so now, after you've paused it, what happened? All right, what did you find out? Well, you should have found out that you can't even multiply the matrix B times A because the sizes don't match up. All right, taking a quick look here, we said that B, matrix B is a 3 by 3, and matrix A is a 2 by 3. And since these numbers here do not agree, we can't even multiply it. It doesn't even make any sense to multiply B times A. All right, so that leads us, that's an obvious example that leads us to the next point, that the commutative property does not hold in matrix multiplication. And I've got that listed here under number 3. Commutative property does not hold. In other words, A times B does not equal B times A. Now there may be special cases to where A times B does equal B times A, but that's not true in general. Most of the time it is not true. But the associative property does still hold. If you were to multiply A times B and then multiply that result by C, that would be the same result as multiplying B times C and then multiplying by A. but the order of that does matter, right? We're doing a left multiplication of A, right? That's not the same thing as B times C times A. So the order of how you're putting those matrices does matter, okay? So don't make that mistake, right? It has to be in the same order, but how you're multiplying those can be rearranged. And then the distributive property also holds. If you were to add the matrices B plus C first, and then multiply it on the left by A, that would result in the same thing as if we were adding this, taking the sum of the products A times B and A times C. Okay. There's also the property of the identity matrix. Now, the additive identity matrix is just a matrix of all zeros, right? Because 0 is the additive identity of real numbers. For the multiplicative identity matrix, when we're multiplying matrices, the identity matrix is a square matrix that has a diagonal of all ones, right? So the diagonal here consists of all ones. Everything else are zeros. Okay, and this is just a generic n by n size identity matrix. To be more specific, if we were talking about a 2 by 2 matrix, the identity matrix would be 1, 0, 0, 1. A 3 by 3 identity matrix, right, would consist of a diagonal of all ones, everything else zeros. That's the identity matrix. Identity meaning that if you were to multiply this identity matrix by any matrix, by any other matrix of the same size, then you would get the same matrix. Multiplying by the identity does not change the matrix itself that is being multiplied by, right? The multiplicative identity of real numbers, right, is just 1, right? 1 times anything is itself, right? 4 times 1 is still 4. That's the same concept that we have here in the identity matrix. If you multiply the matrix A times the identity, you're still going to have the matrix A. And that's in any order of your multiplication, whether you multiply I times A or A times I, that's still going to result in the original matrix A. All right, let's take a look at some additional examples just to give you some extra practice with multiplying these matrices. Okay, first identifying if you can multiply them and then actually doing so. In this case, in this example, we have a 2 by 3 matrix, 2 rows, 3 columns, and it's being multiplied by a matrix of 1, 2, 3 rows and 1, 2 columns. So we have this 3 by 2 matrix, and so can we multiply these? All right, the number of columns of the first matrix is the same number as the number of rows of the second matrix. So yes, and the resulting matrix will be a 2 by 2. Right, when we multiply this, we'll have a 2 by 2. So we're going to have 4 entries in this. Okay. All right, and you don't have to do that scratch work out to the side, but I think it's helpful until you get comfortable with it. It's very easy to make a mistake if you're trying to do all of this in your head. Right, but we take the first row of the first matrix, multiply it by the first column of the second matrix. I'll come out to the side and multiply 2. Right, 2 times -1, 1 times 4, and 2 times 0. That gives -2 plus 4 plus 0, which is 2. Okay. Once we multiply the first row by first column, then we will multiply first row by second column. So 2 times 2 plus 1 times 3 plus 2 times 1. That's 4 plus 3 plus 2, which is 9. Okay, so now we've multiplied the first row by everything. So now we'll multiply the second row by all the columns. That's 3 times -1 plus 2 times 4 plus 4 times 0, which is -3 plus 8 plus 0, which is 5. And then we'll multiply that second row by the second column. That is 3 times 2 plus 2 times 3 plus 4 times 1. 6 plus 6 plus 4, which is 16. And this is our product. 2, 9, 5, 16. Now in our next video, we're going to be interested in finding the inverse of this matrix, right? Since we don't have the operation of division, we can talk about the inverse. And a matrix times its inverse will result in the identity matrix. Okay, not getting ahead of ourselves there. I'll say my last example here, we can see that we have a 3 by 3 times a 3 by 3, but the second matrix is a special matrix, right? Do you see what that is? Diagonal of all ones, everything else 0. This is the identity matrix. That's the I. You can work through the multiplication to get extra practice if you'd like, but we know when we multiply any matrix times the identity matrix of the same size, it will result in that same matrix. So there's no work that we need to do here. We can just copy that first matrix because we know the property of the identity matrix. All right, so we get the same matrix as we got here. And if you were to work through the multiplication, multiplying each row of the first matrix times all the columns of the second matrix, you would see how all that works. And I would encourage you to do that just so you can get a stronger feel for that. Okay. All right, so those are our operations. Next video, we'll look at inverses and the usefulness of inverses for solving these matrix equations that we'll introduce.